interpreting. And then we'll look up at the slides, and then we're going to scroll through this, and we'll move on from there. Okay, so if I'm drawing for A, right, and I wanted to know, does it have a resonance structure, what are you looking for? Now, you may not know all the terms, but you may know what to look for. Right? What are you looking for?
Positive or negative charge.
Positive, negative charge, you're looking for that. Yeah, that's one of the things. You don't have to, though. You can have lone pairs. And everything else that's connected to it has to have a double bond or a triple bond. It has to have a p orbital. So the technical thing we say is it has to have p orbitals, right? So when you look at like this first one, oh shoot, I mean for that to happen, I just wanted to, yeah. On this first one, this is SP what?
On the top.
Yeah, who doesn't know what it is? Let's do that. And tell me what you need to know. I can help you with it. What's the hybridization of that? You guys remember? Yeah, so you just remember, this helps you. There's a hydrogen there, right? So it's got 3 groups, so it's sp2, right? And because it's sp2, one of the p orbitals, the one that's my pinky, right? When I'm drawing it on my fingers, that's the unhybridized orbital. So it has to have one of those in order to be involved in resonance. Okay? So you see this one here. This is sp2. This is sp2. And this one, that's also sp2, right? And so because it has 3 groups on it, there's nothing drawn there. That's why there's a positive charge. And so if I draw the resonance structure, the electrons can move like that. You always start the arrow on the electrons, right? And you end up where you want the bond to be. Now, some people will do this. You know, they'll draw that arrow to that. I don't want you to do that. I just want you to draw it where you're going to draw the bond. Okay? Okay. Some drawing programs have shifted to doing like I've shown here, and then they'll draw a line like connecting the two to show where the bond ends up. But I don't like that method either. I'm old school. One arrow, show me where the bond's going. Okay, so let's go back through B. Does B have do you want me to draw the resonance structure? I didn't draw it. We can draw it. I have a lot of practice on that, but if I'm going to redraw that, then it goes like this. That's a CH3. I'm just not going to draw it. Okay, so when I drew that arrow, right, what does that mean about the electrons? What am I drawing now?
The double bond going
from the left side?
Yeah,
like that.
To the top, and then you're adding a positive charge.
Yeah. Now, why is there a positive charge there now? What's that? Yeah, but I mean, that's right. It has 3 things on it, but when you break a bond and you pull the electrons away, that's why it becomes positive. You're taking the negative charge away. Okay, so what about B? What was wrong with B? Resonance? No resonance? No resonance? Why? Yeah, this guy right here is sp3. So there's no way for the electrons to get across over there. So it doesn't have delocalization, doesn't have resonance structures. Okay, so this next one was a little trickier. How do I do that one? And then there's a rule about this that we'll talk about. But
You take the lone pair on the nitrogen.
yeah, and you go like this, right? But can you just leave? Because right now, this carbon here has 4 bonds. So what do you have to do?
Move the double bond.
Move the double bond. And this is one of the patterns, like, when you don't have to move 2 things at one time, it's pretty easy to see where stuff goes. But this is one of the patterns that you should just memorize how it happens. It's just so you can see it. It's a lone pair and a bond. And when the lone pair moves in, the bond has to move out of the way. Okay? So when you draw that structure, so what I'm looking at is this and this. Those are the things that, well, actually, let me do it with a highlighter color. I'm looking at that and that. Okay. That's not even that good. Hang on. There we go. Yeah, this guy, oof, nice. That guy and that guy. That's what I'm looking at. When I draw that structure for that, it's going to look like this. And then we'll talk a little bit about why that is confusing. I'm going to draw those out like that. Now what am I missing?
The positive charge on the
Nitrogen sharing another pair, so it's positive. And what else? Somebody else give me an answer.
Negative charge on
Yeah, negative charge on the lone pair, like that, okay? And something to remember too, like the charges, you notice like a plus minus is 0, right? I started with 0 net charge. I should end up with 0 net charge. So one of the things they say in the book is you can't create charges, right? Or you can't create electrons. And so the overall charge always has to be the same. Okay, so what's weird about that? Why does anybody see what's weird about this? What's its hybridization, the way it's drawn? How many groups does it have, right? So we draw it out. Got the lone pair. I got like this. Got 4 groups, right? So this is what people usually say, okay? It has 4 groups, and normally that's not involved, but if it has a lone pair, right, and that can be involved in resonance, then it's involved in resonance. It participates. So that atom actually changes its hybridization in order to participate. Okay, so it can change its hybridization, it will. So the way I usually just say it is simply, if a lone pair can participate, it will participate, right? Ultimately, the reason for that is it's more stable that way. If it can delocalize its electrons, the structure will be more stable. So that almost always happens. Now, it's not necessarily, we talked about major and minor contributors the other day. It's not necessarily a major contributor, but it's a contributor. It helps with the stabilization. Okay, I'm going to move on from there. I just wanted to review. Those are some basic things we just needed to review. Did we finish this one? Let's see, where were we? Yeah, we talked about that. Yeah.
That's where we were.
Yeah. Yeah, so how does a lone pair participate, and how does it make things more stable, right? So I have a lone pair here, and I have a carbocation, if you guys remember that word, carbocation. And, oops, didn't mean to do that. What can happen is this pair of electrons can move in like that. And that gives us the structure we see on the right. These resonance structures go both ways, so if I were to go in the other direction, right, I could take this pair of electrons and move it back like that. So these are actually, this resonance, right, back and forth kind of idea. So you could go either way. So you notice, like in one of the structures, positive charges on the nitrogen, and the other one, the positive charges on the carbon, right? So in essence, in the hybrid, well, like if I were to look at like the average structure for these, what I would find is that it looks something like this. And there's a dashed line here, and there's my hydrogen that's here. Right, I'll have a partial positive charge here, and a partial positive charge here. So the point of delocalization is, right, is it spreads that charge out, and the more charge you have in one place, the more reactive things will tend to be, and less stable that things tend to be. Right? So the more charge you have in one place, the more unstable it is. So if you can spread it out, it's more stable. I usually give this analogy, like if I threw a $100 bill on the table in the middle of you guys over here, and said, you know, ready, set, go, and I threw $100, what would you do? You would just like shove people out of the way. Well, you'd probably figure it wasn't really a $100 bill, but
I think it's a demonstration.
yeah, no. Oh, I have a 50. Yeah, fat chance. Yeah, so but the analogy works, right? If I throw a $100 bill there, you're all going to go try grab it at the same time. Whoever's the quickest or the meanest or whatever to get it. Very, very unstable situation. Now, how many pennies is $100? 10,000 pennies? If you threw 10,000 pennies on the table in front of you, what would you do? You'd be like, what? And you'd be like, I'll just take some of these, but I don't really want all these pennies. And so if you spread that same amount of money out, same amount of charge out, it's a lot more stable situation. It tends to be less reactive in some ways, okay? Okay, so that was the idea. Oh, so, cheers, we even see it in structures like butadiene. That's the name of this structure, 1,3-butadiene. So if you look at butane, right? Now butadiene has a single bond in the middle here, right? Has a single bond right in the middle. And if you look at butane, that bond is 153 picometers. Now you know what a picometer is? It's a tiny, tiny measure. It's a 10 to the minus 12th meters. Okay, so 153 picometers. Now, if you look at butadiene, it's 147 picometers, right? Part of the reason for that is this resonance structure that you get here. Like you move the electrons, right, from, well, actually, let me do it like this. You move these electrons from here to here. And then you have to, because you're moving a pair of electrons, you're going to push this pair of electrons to here. So you'll have a negative charge here and a positive charge here. Now, they didn't draw the lone pair as dots here. It's a, darn it, I did the recording stuff. If you take, there's not too big of a gap in there. NH3 plus bonded, so this represents both, and you add it to water, what you should get out of that is NH2 with the lone pair plus an H3O plus. Okay. And what I want to do is show why this is more stable when it's like that. So on the next slide, you're going to make a change. This is, this is supposed to be H3O plus. So this is after it's transferred. And then I'm left with, oh no, I'm sorry, I did do it right. I just didn't draw the H3O plus on the other side. That's what I'm missing. So I have the acid-base reaction, and I left out my H3O plus here. Okay, so this is what happens for aniline when it reacts with water. And what I want to do is draw its resonance structures, just so you guys can get some practice. So I drew a bunch of rings down below, so you won't have to draw the rings. You can just draw the bonds in, okay? So to start with, the first structure is this one. So I'm going to just redraw what's over there. And then I'm going to take the electrons and I'm going to move them in, right? And then these will move out. So what am I left with? All right, you redraw it. And you only change the parts that you drew arrows with. Now what? What's missing?
Negative.
Charges, negative charge and a positive charge, right? Because overall, this one's neutral, so I have to have a positive charge when I make the negative charge. And as a practice, go ahead and try to get ahead of me here. I'm just going to start doing it. Well, it's not going to charge on it like that. That's where I end up with. It's a half an hour. I'm so tired. We'll finish though. I still have another lecture to lab this afternoon. I'm just like, oh. And then there's a basketball game tonight. I don't know if you guys follow high school basketball. But Emmanuel has a home game in the state tournament still, so they're in the fourth round. The next round's the final. And then Danuba's still in it, but I don't think they have a home game. I'm not sure. And, you know, Danuba played Emmanuel for Valley Championships. It's potentially they could both go on and become state champions. It's kind of crazy. All right. You guys get that okay? Follow the drawing? Okay, good. It's important because we're going to do it next time. Okay. I'm going to skip some of this because we've talked about a lot of, well, actually, yeah, just real quickly. Even molecules like this, where you have a 1,3 cyclohexadiene, you notice how 1, 2, and 3, and 4 are conjugated. That's the term. They have resonance with each other. And then in 1,4 cyclohexadiene, right, they're isolated. In isolation means they have an sp3 carbon in between them. The isolation between the carbons means that cyclohexadiene is less stable than the 1,4 is less stable than the 1,3 because it has resonance. 1,3 has resonance. Okay? So you can look at double bonds and find that this double bond is more stable. These double bonds are more stable than these double bonds. Okay. Oy. You know, so they have this term up here, polyenes, right? A polyene just means it has more than one double bond. So this is a diene, there's trienes, there's tetraenes, and then they just kind of get crazy. So I'm not going to draw the resonance structure. I'll let you look at those slides. Yeah, this is actually an important one, so I'll mention this one. This is a benzylic carbocation. So a benzylic carbocation is a carbocation attached to a carbon next to the benzene ring. Okay, so it's a carbon not on the benzene ring, but it's a carbon next to the benzene ring. And this is what the electrostatic potential maps look like for the benzylic carbocation versus that methyl carbocation on that cyclohexane ring. Now, do you guys, I don't really talk about these that much in lecture, but are you guys familiar with this from looking at it in the book? What this represents is how the charge is spread on the molecule, right? So blue is positive charge, red is negative charge, and then it's essentially Roy G. Biv in between. So green in the middle is kind of neutral, yellowish is kind of neutral. So you'll see this is kind of a yellowish green or maybe a blue green. These are in the neutral ranges. If you look at the molecule on the right as an electrostatic potential map, the dark blue up here means the charge is all up in this half of the molecule. If you look at this electrostatic potential map, what it shows is that the blue actually spreads all the way down into the bottom of the molecule. All right? And just, I'm not going to draw all the resonance structures for this one because it will take some time. But it's the exact same kind of patterns that we've looked at before. This pair of electrons can move here, and when it does, where does the positive charge move? The one on the left, right? Like there, it'll be right there. And then this one can move, and then the positive charge would be here. And then this one can move, and the positive charge would be here, like that. So you get partial positive charge spread around the molecule, and it's interestingly not on every carbon, so that's why these two aren't as blue as this one is. So the delocalization of the electrons, if you draw all the resonance structures out, shows positive charges here, here, and here. Okay. All right. So I'm going to skip drawing all of them, unless you really want to draw all of them. I don't want to draw all of them right now. You can fill them in. Okay. I do want to point out one thing, though. In order for this carbon to participate in the resonance, it actually has to be flat with the rest of the molecule. And if you look over here, this is what the p orbitals look like in order for it to be flat. Okay. So that part of the molecule is actually, that whole molecule sits in one plane. All the hydrogens that are on that part of the molecule are in the same plane with each other. Okay. So you still have to know Markovnikov's rules. I don't say that the class is cumulative, but basically the class is cumulative because everything sort of adds on top of each other. So when you look at this reaction, and we're thinking electrophilic addition of a hydrogen halide, that's the reaction. I'm adding HBr to this double bond, right? There are two possible products. You guys remember the reaction? Just a HBr on a double bond. Right? And it normally likes to put the carbon with the most hydrogen gets a hydrogen and the other one gets the halide. Right? So actually there's two possible products here. There's one with the hydrogen on this carbon, that's this one here, and there's one with putting the hydrogen on this carbon, and that's this one here. Right? So there's the two different products. And normally, one of them's a major, one of them's a minor, unless they're both the same, right? And then it's 50-50. So what do you think this one's supposed to be? 50-50, because, right, so it's not, though. Here's why. The only product you get is this top one. This is the only one you get. The reason for that, let me make sure I don't have that on the next slide, hang on. Yeah. Is that when that hydrogen adds, right, it forms a carbocation that can delocalize into the ring. And the reason for the difference, like the major and the minor product, was stability, right? If you had a tertiary carbocation, that would have been more stable. A secondary carbocation is more stable than a primary carbocation, that kind of thing. Well, in this instance, there's this carbocation that you form, and that carbocation, I'm not going to draw all the resonance structures, but I drew them there so you could start them anyways. Right, I can go, oh sorry, I didn't mean to draw all those. I can delocalize that charge into the ring. Right? So, by having this positive charge next to the ring, right, it can delocalize that charge into the ring. And because it's more stable, that ends up being the major product. Does that make sense? Yes, no, no? Yeah? You got it? Okay, so let me go back. Let me go back to the first slide, because I want to make sure you guys understand. I see the looks on the faces like, well, I kind of don't know. And all I want you to do is say, yeah, do another example, and then I'll understand. That's all I'm looking for. I don't expect you to like. By the way, you guys know the rule of lecture is the most you'll ever get out of lecture is 20% of it. That is the most you ever get out of it. The best, I could give my best lecture of my life, and I know students might get 20% of it. So if you don't get it, it's in the other 80%. If you ask me to say it again, maybe you'll get 40% of it, right? And then the rest of it you'll just fill in. You'll be like, oh, I remember that now. Okay, let's just go back for a second. If I think about mechanism, and this is what helps me all the time, this is going to go like that, right? The double bond in the mechanism attacks the hydrogen, and then the electrons break off and go to the bromine. I end up with two possible intermediates, and they're going to look like this. Because the hydrogen can add here. I'm going to put an R here so I don't have to draw the rest of it. And then if I do that, where's the positive charge? It's on the other one, right? Now the hydrogen could add on the other side. So it could go like this. And if that happens, where's the positive charge? On the bottom one, yeah? And this is my R over here. Okay, so remember when we were looking at these electrophilic addition reactions, we always said, we talk about carbocation stability. Like tertiary, that's where the halogen goes if there's a secondary. Tertiary versus secondary. So if I gave you something like this, and then we did the reaction with that one, you would have said, oh, this is the major product. With HCl, for example. Do you remember that? That's the major product for that reaction. So if I did HCl goes to this. If I did HCl from this, the major product would have been that. And the reason we said that was that when this first step of the when the mechanism happens and you have your first step of the mechanism for this top one up here, the first step of the mechanism does this. And that carbocation is more stable than a secondary carbocation. So when we're looking at major products in these reactions, it's the creation of the carbocation which decides the major and minor product. You always want to make the more stable carbocation. So the rule was, in Markovnikov's rule, right, the carbon with the most hydrogens gets a hydrogen, and the halide goes to the other one. But the reason for Markovnikov's rule is the carbocation. You're always forming a more stable carbocation in Markovnikov's rule. So that's why when you had something like this, and you said, what's the major product? It was 50-50 because they both were secondary. And you form two secondary carbocations, you get equal amounts of each product. You get one with the halogen in the middle, and you get one with the halogen over here, right? So then you would have like this. Oops, didn't mean to draw it upside down. That would be the other one. Okay, so now we have another way to tell whether or not carbocation is going to be more stable, and this doesn't follow Markovnikov's rule. So this is why it's important to understand where Markovnikov's rule comes from. It comes from carbocation stability. And when we look at this reaction, there's two possible carbocations. There's one that's here, there's one that's here. And this one, right, can delocalize into the ring, and this one can't delocalize because that's sp3. And it's isolated from the resonance structures. Okay, so as a result, because this one can delocalize, and we can draw a bunch of resonance structures from it, that's the major product. That help? A little? Yeah? No? We can spend more time on it later. We can talk about it again. But we just need to, get these things worked out, because this will help you get through the rest of the exams and classes and stuff. And by the way, so there's this young lady who is in the OChem class. She's happy to come on Sundays and tutor you guys. All right, so if you come in on Sunday, she'll be there and help you guys out. So, except for this Sunday, on Friday, she's getting a wisdom teeth out. She says she's 50-50 on whether or not she's going to come in on Sunday. I'm like, yeah, you're probably not going to be there. But she was supposed to get them out this last weekend, and then her insurance and all that stuff. Or lack of insurance, I should say. Okay, so let's talk a little bit about carbocation stability with resonance, okay? So, primary allylic carbocations, right, are not that stable, or not as stable as secondary. It's not as stable as tertiary. So the most stable carbocations are the ones still with the most alkyl groups attached to it. In terms of the big picture, a primary allylic carbocation is between a secondary and tertiary carbocation in stability. So if you were to think about like something like a scheme like this, I have primary carbocation, I have a secondary carbocation, I have a tertiary carbocation, right? This falls in between these two in stability. And these are all more stable. Okay. So in terms of stability, resonance gives a lot of stability to the carbocation. So you have to look at that now. Instead of just looking at Markovnikov's rule, you have to look at carbocation stability and resonance. Okay. Some of the most stable carbocations are the ones that are benzylic, right? So this is a primary benzylic carbocation. It also falls in between a primary and a secondary and tertiary. And then these are all more stable. This tertiary benzylic carbocation was so stable. That's the first carbocation they were able to actually isolate and study. It'll just sit and exist on its own. Okay. Okay, so another thing that to look at. Let me draw this out on another slide, actually, because, yeah, I'm just going to draw the whole thing out. It's actually drawn on the next slide, but I just want to do it. So we're going to do an electrophilic addition on a conjugated diene. Okay, conjugated diene just means the double bonds are next to each other. So here's 1,3 butadiene, and I'm going to add HBr to it. And to sort of emphasize the mechanism and why it's important, I'm going to draw the whole thing out. Okay. So what's the first step?
The group attacks the hydrogen.
Yeah. So the pi bond.
Yeah.
Yeah. What did you call it?
The group.
The group. I thought you said the grill for a second. I'm like, what? Well, I actually like it. So I'm gonna go like this. Yeah, like that, right? So that'll form a carbocation. Now I could form a primary or I could form a secondary. Which one do I form? Always want to form the secondary if you can, right? The primary is where the primary carbon is where my hydrogen will attach. So it'll do this. Since I did it like that, where's the positive charge? It's on the number 2 carbon right here. Yeah? So let's number these. That helps. 1, 2, 3, 4, like that. Okay. Now this is what you have to recognize. This structure has resonance, right? So what do I have besides the carbocation in solution right now? I'm missing something. I didn't draw it. Like in the product, there's like one more thing. The bromine, yeah. I have a bromine. So there's a Br minus, okay? So the Br minus could immediately attach here, and then I would end up with one of my products. I'll just tell you, this is known as a 1-2 addition because I'm adding on 1 and 2. Okay. The bond you first add to is given the number 1 and 2, and then the rest of them are 3 and 4 and 5 and 6, because you can have like multiple bonds. So this is known as, oh sorry, I didn't mean to draw the positive charge there. I meant to draw the product there. This is known as the 1-2 addition. Now, technically, it's the 1-2 electrophilic addition of a hydrogen halide, but yeah, it's a 1-2 addition. I guess I could have spelled it all out. Probably just enough room. It's also known as the kinetic product, and I'll explain that to you in a second. It's the kinetic product. But it's called the kinetic product because it's the one that forms fastest. Why do you think it might, well, let's go into it just a little bit. Why do you think it might be the one that's formed the fastest? Okay, we're going to play a game. I love using money. Thank God I got 2 $1 bills. Okay. We'll give you $2. Actually, I'm not. We'll get back in it. Actually, I have friends that'll find you. No joke, I once had a girl whose family had ties to the Armenian mafia. They paid that off for one time. Okay, you're in trouble. I'm like, we're okay. We're not going to have that kind of trouble. Like, they weren't threatening me. They were like, if you need help, I need help. Okay. Okay, so I'm going to give you $1. This is the hydrogen, this is the halide, right? And I'll stick this one in your pocket. Which pocket am I going to stick it in? This one here, right? The one that's close. I'm not going to reach around. That's a little too weird. Okay. So this is. So we're gonna do this again. Oh, maybe you should stand up. And then turn this way for the audience. Let's stick your arms out. And then flat. Yeah, just put your arms out. I just want to make it look silly. So we're gonna do this hydrogen halide addition, right? Stick the other one in his pocket. Which pocket do I stick it in? That one there. Why do I stick it into that pocket? It's the closest, right? This is the bromine. The bromine formed near that pocket. So it's going to go right into that pocket. It doesn't go, oh yeah, I'll just stick it in the other pocket because it's way over here, right? I only do that with my wife. That's kind of weird. Like she asked for my car keys, right? All right, TMI. Yeah, so that's why it's the kinetic product. It's the one that forms the fastest. It's called the proximity effect. Not in your book, probably. Now, here's the thing. This structure has resonance, right? So I can draw a resonance. Oh, shoot. I can draw a resonance. Can't get the screen to move. Come on, move. There we go. This has a resonance structure, and so I'm going to draw it. And in the resonance structure, what's going to happen? Double bond's going to move to the middle, right? And you're going to end up with this. And then the halogen can add. But this is a lot slower because, right, the bromine formed on this side, and now it's adding on this side. It's slow. That's why it's slow. It's not called the slow product, by the way. I'll tell you what it's called in a second. So once that resonance structure forms, this bromine can attach over here, and then I end up with another product. And this is known as a 1,4 addition. It's also known as the conjugate addition. Ooh, I forgot. There's another name for the other one. It's also known as direct addition. Sorry. There's all these words. So one's direct and one's conjugate addition. And it's called conjugate addition because when you have multiple resonance structures, that's said to be conjugated, so we say it's conjugate addition. Now, it turns out double bond stability. I don't know that we talked about this, and it's actually a subject for a later chapter, but I do want to mention this. If I look at a double bond, let's say I have something that looks like this, and something that looks like that. I think let's do one more. All right. It turns out this double bond's more stable. And the more internalized the double bond is, the more stable it is. So the more alkyl substituents it has, the more stable it is. So this double bond turns out to be a more stable product. So this is actually known as the thermodynamic product. It's the more stable of the two products that you can form because of that double bond. Okay. Which product you actually get the most of, it's kind of beyond the scope of this class, but it depends on what temperature the reaction is run at. If you do it at low temperature, it's always kinetic. If you do it at high temperature, it's always the most stable, thermodynamic. That's actually a subject, a big subject in the other courses that we teach here. But yeah, you get two products. One's more stable. This is what I want you to know. Right? You get two products. One forms quickly. It's that proximity effect. Right? And the other one's actually more stable. And then like why temperature affects all that, you need to know quite a bit of more chemistry before we can do that kind of stuff. That's why it's a subject of the other course. Figure out what this means. Escape dot return. Is there an escape button on here? No. Oh, return. I don't know what I was doing. Something different. Okay, let's see what else we have. So I already did that. Oh, that was it. That was whole. Oh, I got 3 minutes. I'm gonna hand out slides, and then we'll call it a day. And they're hermetically sealed, so they're not covered with my disease or whatever I have.
Let someone else pass them out.
Yeah, so I'm just gonna tear it open, dump them out on the table. Here, I'll take the top copy. And you guys can have the rest disease-free. I don't know why, by the way, they print it so wide. They're like super extra wide. I didn't do that. Yeah, so grab some notes on your way out. Homework, right, is due on Tuesday, but it right now is the rest of this chapter, so you might as well get started on it. And then I'll have a little bit more. We'll do more on this. Yeah, I just assigned problems 1 through 21. I'm sorry. For the next chapter, I'm like, just do them all.
You're turning in homework today, though, right?
Yeah. So it's like 4 problems I think, from last week. You turn in your homework.
So we're all supposed to finish chapter 6, right?
Huh?
We were supposed to finish chapter 6?
Yeah, finish 6 and then do the 4 problems. I assumed you finished 6 because it was a quiz. But... Oh, I should stop that.